Welcome to Semantic Web Technologies, lecture number 4, Knowledge Representations, part number 8. In the last part, we have learned about the resolution technique or the resolution method for automatic induction of a tautology or a contradiction. And we have learned this for propositional logic, how to prove that a knowledge base is correct, how to prove that an implication is correct, or how to prove that a fact is implied or entailed by a given knowledge base. And now we want to extend this methodology to first-order logic. So in first-order logic, it gets a little bit more complicated because here we have variables and functions inside our clauses or inside our canonical normal form. So what we see here, for example, are two clauses. And these two clauses, of course, they contain here predicates, they contain variables, they contain functions. And the trouble is, okay, how can we here identify literals that are negated and not negated and then resolute them or do the resolution step and identify them beforehand? So it's a little bit complicated. But what we can do is, of course, we can do substitutions. And this means that, for example, we can substitute variables by constants. And also we can substitute variables with functions of variables. So, for example, here, we can really achieve a resolution by substituting the variable x with the constant a. Then you see here we have the predicate p and here not p, and both in the first place will be an a. And secondly, we can substitute the variable z with a function of a variable y, here f of y. And then, of course, with these substitutions, we can then make a resolution because we identify that this and this can be removed. But of course, also in the remaining parts of the clauses, the same substitutions have to be applied. Therefore, the result here also changes. So f of x will be f of a because x has been substituted by a. And here, r of z will become r of f of y because z has been substituted by f of y. So in general, you call this technique substitution or unification to identify possibilities where you can apply a resolution in first-order logic. So the unification of terms is defined in the following way. Let's say we have two literals, L sub 1 and L sub 2. And what we want is we want to have a variable substitution sigma. So variables can be substituted by constants or by functions of variables. And this variable substitution sigma should be applied to L sub 1 and L sub 2, to our two literals. And the result should be that L sub 1 and the substitution is equal L sub 2 with the applied substitution. So if there is such a variable substitution sigma, then sigma is called a unifier of the literals L sub 1 and L sub 2. So the unification algorithm works in the following way. So given we have two literals L sub 1 and L sub 2, what we are looking for is a unifier sigma for L1 and L2. We have to consider several cases. So first case, L1 and L2, they both are constants. Then they are only unifiable if L sub 1 and L sub 2 really are the same, when they are equal. Otherwise, you cannot do a variable substitution. So if L1 is a variable and L2 is an arbitrary term, then they are unifiable if for variable L1, the term L2 can be substituted. And variable L1 does not occur in variable L2. So this is mandatory. The variable you want to substitute, or then the variable must not occur in the term L2. Otherwise, it's not unifiable. And the third case we have to consider is if L1 and L2 are predicates or functions. So, for example, we have here predicate L1 and predicate L2, and they have the arguments s sub 1 to s sub m, and here t sub 1 and t sub n. And they are only unifiable either if they are really both the same, so pl sub 1 equals pl sub 2, or the arity of both is the same, so the m is the same as n equals m. And all the terms that you have here, s sub I and t sub I, they must be unifiable. It means a term s sub I must be unifiable with a term t sub I. Only then both are unifiable. Only then these literals are unifiable. Let's take a look at a few examples given here in the table. So let's consider here in L sub 1, we have p of the variables xx, and we have on the other hand p on the constants aa. Then it's pretty simple. We can make a unification where we substitute variable x with constant a. So this is the substitution here. We substitute x with the constant a, and then they are unifiable. No problem. Look at the second row there. It's a little bit more complicated. We again have p of the two variables x, and here we have p and two different constants, a and b. So the trouble here, you have the same function, and you have to either substitute x with a or x with b. So not both at the same time. So here it's not applicable, and you cannot unify these two terms. Here L sub 1 and L sub 2 are not unifiable. In the third row, there it's much more easier because we have here different variables, and here variable x can be substituted with constant a, and variable y can be substituted with constant b, as you see here. So this is pretty easy unifiable. On the other hand, this also holds, for example, if you have here two different variables and here twice the same constant, then you substitute simply x with the constant a, and you substitute y with the constant a, as you see here, and then both are unifiable. Okay, more complicated, we have here a predicate p, function f of variable x, and a constant b. And here we have predicate p, function f, and here we have variable z. And this function f is a function of constant c. So the first thing that you can do, for example, here you also have f of x and here f of c. You substitute variable x with constant c. And the next thing you can do, you cannot substitute here a constant. You only can substitute a variable here, and then here you can substitute variable z with constant b, and then again both will be unifiable. Okay, let's take the function on the second place. So here we have a predicate p of variable x and then a function of x, and here we have a predicate of the two variables y and z. And what you can do here, for example, you can substitute this function x with another function y, a variable of course, and you can substitute here variable z with f of x. And it must be f of y because you have substituted here fx with y. So you have to take this into account. So make one substitution after the other before you do, in the end, the unification. On the last example, it's not, again, possible to unify both of them. Here we have the predicate p of the variable x and the function of x, and here we have the predicate of the two variables y, y. And yeah, you can substitute, of course, x with y. And then you have here, again, y, and you have to, it's not possible to make a unification here. Okay, so let's come back to our original problem. As you can see here, these two clauses are pretty easily unifiable. What we do here is first we substitute x with a constant a, that is over there, and then we substitute z with a function f of y here, and then we can make a unification, a resolution, because then we have here a literal and a negative literal, so there can be a resolution step. Let's try to make this resolution then in a real example. So let's take this example. We have the knowledge base given here, split it in a T-box with terminological knowledge and assertional knowledge. And in our T-box, there we make clearly that here is a human, and a human is defined that a human always has some parents. And we define what an orphan is, and an orphan, of course, is a human whose parents are not alive anymore. And then we have the assertional knowledge in the A box, and we say that Harry Potter is an orphan, and we say that James Potter is a parent of Harry Potter. And the question is now, given from these two facts, that Harry Potter is an orphan, then James Potter is a parent of Harry Potter, and we say what an orphan is and what a human is, can we deduce from this knowledge base that James Potter isn't alive anymore? So let's try to do this. So what we have to do is we have to prove that the knowledge base entails that James Potter is not alive. So we have to prove that the knowledge base implies the assumption that James Potter is not alive, that this is a tautology. And to do that with a resolution, we have to negate this statement. So we have to prove that the negation of this statement, so we have put braces around there and put a negation in front of it, this should be a contradiction. What do we have to do now? Of course, simply we have to transform this into a canonical form, into the clausal form. This is, of course, complicated. And, of course, we can make lots of errors within that. So first thing you know, you have to put the negations inside. So we have to compute the negation normal form. And then after that, you have to compute the so-called prenex normal form. And here I have already given you the prenex normal form with all the quantifiers we have here. And all single clauses have here different variables where the quantifiers were bound to. And as you can see here, it's getting longer and longer. Next step would be then this column normal form, and after this column normal form, we had the conjunctive normal form or the clausal normal form, and I give you the finished clausal normal form. Of course, you can take this in the exercises and can transform it by yourself with the rules given in the last part of the lecture where we have learned about the canonical forms, and you should do that. So this is the clausal form, and of course, the clausal form then also can be written with the curly braces. And there we see we have 1, 2, 3, 4, 5, 6, 7, 8 clauses. And on these clauses, then, we can apply resolution for first-order logic. OK, we have our knowledge base with these 8 clauses. And what we do now is we try to identify 2 clauses that can be combined in a resolution step. And for this resolution step, for example, we have taken clause number 3 and clause number 7. And we have substituted here, orphan xy, we have substituted the variable xi with Harry Potter, and we have substituted the variable y1 with James Potter. And then, if you do this, you can, in a resolution step, for example, remove the predicate parent of, because you have it one time here not negated and here negated, and you have here Harry Potter and James Potter substituted, and it can be removed. So you can deduce from these 2 clauses that not orphan Harry Potter and not alive James Potter. Of course, you have also consider the substitutions and the unifications in the other parts of the clause. So number 9 is the result of the first resolution step, and we add number 9 to our knowledge base. Now we have to find 2 new clauses that can be combined. And now we can combine, for example, number 8 and number 9, simply because we see here, we have here the function alive and here not alive. And we have, again, here the same constant inside, so the same individual, James Potter. And again, we can see here, we can make a resolution step between 8 and 9, and the result will be here, not often Harry Potter. Okay, not often Harry Potter is put into the knowledge base. Let's look at 2 other clauses. And then if we also consider not often Harry Potter, and here number 6, often Harry Potter, if we combine these 2, then it's pretty easy. We have here the negation, that Harry Potter is not an orphan, and here we have not the negation, that Harry Potter is an orphan, and in the resolution step, we will come up with the empty clause. And what we have seen here, or shown here, is that this knowledge base is a contradiction, which means, on the other hand, that our previous assumption of the not negated statement was a tautology. So, therefore, we can deduce that James Potter is not alive. So, this is the resolution as a method for proving the entailment of new facts from knowledge bases. Resolution itself has, of course, certain properties, and one of them is the so-called completeness of refutation. So what does that mean? So if a resolution is applied to a set of clauses that contains a contradiction, then there always exists a finite number of resolution steps to detect this contradiction. But the problem is, of course, the number that is required or needed to find the resolution might be pretty high. So it's not an efficient method. On the other side, resolution for first-order logic is undecidable. And this means if you have a set of clauses and there is no contradiction in it, then it's not guaranteed that this method will ever end. So you will, until infinity, combine clauses with other clauses and will never find a contradiction, and will never find in a resolution step the empty clause. So therefore, resolution for first-order logic is undecidable. But on the other hand, and this for working in practice is pretty convenient, whenever there is a contradiction, you are able to prove it. And this, of course, is what we want. So, this is one method to automatically prove this entailments, and that entailments are true. But there are other methods. So the method we have seen here works for first-order logic, works for propositional logic. For description logics that we need for knowledge representation, we will apply another method, which is a little bit easier. But I wanted you to show the traditional methods for making automatic entailments and give a proof of this entailment. In the next part of the lecture, we will learn about the so-called tableau algorithm, which is a little bit easier and a little bit different, but which can simply be applied also to description logics. And description logics will also be the next lecture. There you will learn more about description logics and its representation in the semantic web in the form of the web ontology language. But for that, we need the tableau algorithm, and this will be the next part of the lecture.